Hey, how's it going, everyone? It's been a long time since I've uploaded. I've been busy with my first job, and speaking of which, I'm currently looking for work, so if anyone has an opening, just let me know. Um, so I've been doing more firmware development these days, and so I figured I'd cover some of Xilinx tools, and in particular, I want to cover something that is super cool and there doesn't seem to be any information about how to do this online. It took a lot of work for me to figure out how to do it, and I went ahead and did the legwork to make it work with the PYNQ open source platform, which is a Python productivity platform, and you can run it on pretty much any Xilinx SoC evaluation board besides the 102. Um, and it will allow you to use Python to interact with different firmware designs. It's pretty neat, and I can show you how all that works later. Um, but the topic of this video is going to have to do with these ILAs and smart links, because it's a pretty typical thing. We use them all the time if you're a firmware developer. So I'm going to show you how to drop a smart link straight into your design, and just how easy it can be, at least if you're using PYNQ and the code that I wrote. Well, the code that I forked from Xilinx XApp 1251 application note. I had to make a few changes to it to work with PYNQ, but everything seems to be going pretty good. We can start off just by kind of going over design. I needed something to debug, so I made something real simple. We're just debugging this counter, and we have some control signals. There's a count enable, and there is a clear, and then there is a load enable, and then a load value. It's 16 bits. So this is a 16-bit counter, and I got a 2-channel AXI GPIO block. Our first channel is just 2 bits. It's our controls for count and clear. And then we have a 17-bit output, where the lower 16 bits is our count value to load, and the highest bit is our load enable. We have a counter value that is going to be coming out of this, as well as a threshold. It's basically just a one-shot trigger whenever the counter wraps all the way back around. This is kind of a side note on these ILA triggers, or just these ILAs being cascaded in this fashion. This is really super useful and handy in the cases where you want to have, a large sample depth for, like for instance on this one, we want a large sample depth. As high as it'll go. Now, if we was to capture all 6 of these probe signals, 2 of them being 16 bits each, it would fill up and use up all of our VRAM. But what we can do is actually have a big sample depth on this one, and then on this guy right here, just have it as small as it'll go. And what you're going to want to do in order to use it cascaded like this is to enable the trigger out port, and then enable the capture control and advanced trigger. You don't have to enable the advanced trigger if you don't use it. Input pipe stages, I highly recommend you set this to 2. And then on this guy, it needs to have the trigger import option. It also needs to have 2 input pipe stages and then capture control. And that's just a nice way of, because I wanted to be able to see this counter wrap around, and it wraps around to 65,000 something. So that's the kind of demo firmware. Now, in order to debug this using Xilinx Virtual Cable, which is what we're going to be using, there are some they do have a Confluence page, and of course they have their application notes. I'll have all this stuff linked in the description. I had to modify this in order to work with PYNQ, and I'll go through some of that. So to add that functionality on the PL side of things is super simple. All you have to do is add a debug bridge. Oops, butterfingers. And so this guy is going to allow us to access the JTAG chain over the network from the PS side of things. And what you're going to want to do is change this bridge type. The code I wrote supports these two. AxiDBScan is used to debug within this same firmware FPGA part. And because you see, it just has inputs, there's no outputs. If you go to the from Axi to JTAG, you'll see it actually has your physical JTAG connections. And so you can route these out and then attach it to a target FPGA and then debug and use this kind of as a smart link. And it's pretty neat because you can instantiate as many of these as you want. So you could have one that's instantiated inside the firmware itself, and then you could have several external JTAG ports, in the case of like a test fixture or for automatic testing or things like that. This is super awesome for making, mainly just test fixtures, but it's still pretty cool. And there's just very little information online. I don't know, it's out there, but it really is kind of figure it out on your own. So hopefully I can help people out if anyone's ever tried to do this and not had much luck. We need another master interface. We just drop that guy down. Now we're just going to connect him up to everything else. All right, and I've already built this firmware, but I will show you how to do stuff on the PYNQ side of things, because if you haven't seen PYNQ, if you haven't heard about PYNQ, PYNQ's pretty cool. This is PYNQ. It's running on my SoC platform, which is an RD Z7 20 board. It's from Digilent. And the operating system, this is the PYNQ project I was talking about. It's a whole operating system image that you flash to an SD card, and then you can boot up your board. And it's pretty neat. It's actually Ubuntu file system on a PyLinux kernel. So you have access to all the Ubuntu repositories, which makes working on this amazing compared to PyLinux from a just dynamically trying things out perspective. So you could come here and download it. In my case, it would have been the image for the PYNQ Z1 board, which is essentially an exact clone of what I got. It's just got a different name. And when you boot it up, you'll be able to, well, initially you'll have to connect it to it with the UART port so that you can set its IP. But it also comes up on the hostname PYNQ, so you can just SSH straight into it. So right here is the Jupyter lab interface. PYNQ runs Jupyter, which is basically like a web-based Python development environment. And the PYNQ library gives you access to, for instance, write to these GPIOs, or in general, just interact with any IP from the PS side using Python in this type of, super dynamic environment. It supports loading bit files. That's what I do up here. I load the bit file directly using Python. And the process for that is, we've already got our things built here, so I'll just go ahead and go through the process one more time. did not mean to do that. Just those two, not that other one. I need that guy. Let's see here, get rid of that guy. We have to export our hardware. And we're going to skip that. I must have made changes somewhere, and that's why it's complaining. So with PYNQ in particular, I recommend getting rid of this underscore wrapper on for the XSA file name, and you'll see why here in a minute. Yeah, I know. Okay. So now that we got that, we have our XSA file here. And what we're going to want to do, if you're on Windows, the simplest thing to do is to just rename it. It will complain, just click yes. If you didn't know that the .xsa file is really just a .zip file. So you can come over here to our Jupyter Lab environment, and you have a little file browser over here. And uploading new firmware is as simple as selecting these two files. So this is the reason I got rid of the underscore wrapper. If the underscore wrapper was there, which is always there by default, thanks Xilinx, this would be called XVC underscore demo underscore wrapper .pet. And the thing about PYNQ is it needs both the bit file and hardware handoff file in the same directory, and they also needs them to be named the exact same, except for the extensions. So getting rid of that wrapper just streamlines it. You just drag it and drop it over here. Oh, it didn't work. That's right. Windows is kind of weird. These are still inside the zip file. So first you have to copy them out of the zip file thing. Yeah. And now the drag and drop should work. Overwrite, overwrite. And that's it. Next time you run this cell, it will load that bit file. And there's a lot of documentation on PYNQ. It's got some it's got some getting started stuff. I mean, it's made for beginners. It's kind of like was the purpose behind it originally, I guess. But I've found it really nice in testing environments. So we got that over here. So the way that the notebooks work in Jupyter Notebook, if you've never used that before, is they have these code cells. So it's basically like, I don't know, it's almost like paragraphs of code. I'm not quite sure why it is like this, but it's pretty neat. You can have markup language interspersed with code. So for instance, you can have my diagram, and there's some other stuff down here. That's pretty neat. You just click play button up here to run it, and it'll just run one cell at a time. And it's kind of like MATLAB in the fact that it keeps all of its environment variables persistently. We can just run this right here, and this will load the bit file. And here's I included a screenshot of the block diagram here. And so yeah, we've got our 2-bit count and clear, and then yeah, our load and our load value. If you just type in a variable as just the variable name as the last line in a cell, Jupyter will print it in like a pretty print fashion. I can just show you. So yeah, this is so the overlay object is returned from actually loading the overlay. So it's like the PYNQ overlay object has like all the metadata and stuff. So for instance, the ol.ipdict will have all the metadata from your hardware handoff file. So for our debug bridge, all of this should look fairly familiar because it comes straight from Vivado properties. So if you select an IP block and you go to properties, this should look familiar, especially the config. All of this stuff is available under the parameters. So some of the stuff on the outermost properties are there. Config's been changed to parameters, but yeah, all that stuff's there. So the code that I wrote, it's the code that I forked from Xilinx application note 1251. Let's pull that guy up. Yeah, it's pretty good. You can go through it and do it the way that they do it. The way they do it is they use a generic UIO driver to access the memory region where the IP resides. In our case, what I've done to the code is I've made it so that it memory maps directly to /dev/mem. So it uses the full deal, and then I just use an offset to the physical address. And the way I've done it is I use Python to go through the overlay object, and I look for any IPs that are debug bridges, and I specifically look for types that are AXI to bscan or AXI to JTAG. And then it'll automatically instantiate the XVC servers that's required to run it. So that's the code that I've contributed. It's pretty simple. You just include this PYNQ XVC utils, and then you can just say pxvc start servers or stop servers, and it should search through there. It'll kill the servers if they're already running. It'll take care of all that, and that's it. It's that easy. You can come over here to our flow or our hardware manager, and connecting up to XVC is a little bit different. You start off by connecting with a local host, local server here, and then to that local server you'll right click it and add a Xilinx Virtual Cable. So you just type in the IP address of your board, in my case it's .46, and I've only got one debug bridge, so it's using the default port. If I had multiple JTAG ports, like external physical JTAG ports, they would just be offset by 100. So each additional one would be count up by 100. And you'll notice that it doesn't open up your waveforms. This is because XVC is a little bit different. It doesn't actually know which debug profile to associate with what, so you have to do that manually. You can select this debug bridge, and you're just going to come down here to the programming file, or to the probes file, and you're going to select. Now these typically live under runs, your latest implementation, and there should be, it's usually called whatever your project is, _wrapper.ltx. And what I've done is I've modified that because I have no idea why this happens, but for whatever reason, Vivado IP Integrator it has a mind of its own when it comes to naming these debug probes in the waveform thing. So I just went ahead and named the ports what I wanted them to be named, so we're just going to use that. But it is automatically generated in that under that runs implementation folder. And we just hit enter. There it goes. Got worried there for just a second. All right, yeah, and that's all there is to it. As far as the, if you're on PYNQ and you're doing it that way, otherwise you could still use my code. It works great on Linux. It's got documentation. The only difference between it and the Xilinx solution is like you have to pass the physical address or the base address of the debug bridge as an argument instead of using the generic UIO stuff, which requires device tree stuff. And you can do device tree overlays in PYNQ, and I've done it before, but this method works nice just for automatically doing it. So we can run them immediate just to see what the status of them is. The only caveat on using this is the JTAG frequency. So the maximum JTAG frequency, well, the only JTAG frequency that this works at is 10 megahertz. The default is 40 megahertz. So it doesn't matter for debugging waveforms and the ILAs like this, but if you was to try to like load like a larger Linux image directly into memory, do keep in mind that it is 4 times slower than the stock speed. And as far as I'm aware, I don't think there's any way to change that. But that's the only restriction. I mean, this is a really awesome thing to be able to do, and it's just wild to me that there's not any good instructions on how to achieve this. I've only tested this on the Zinc 7000 series stuff. I read somewhere where the AXI to B-scan debug bridge doesn't work on the ultra scale MP SoCs, but I'm not sure. I would have to test it. If somebody out there wants to test it, definitely go for it. The only thing I've seen for those is a PCI, like like PCI to B-scan or something like that. Yeah, I'm not sure what's up with that. But anyways, if you're on the Zinc 7000 stuff, this will definitely work for you. The counter is not running because the counter enable is not on. And PYNQ's pretty cool. So this is how you would manipulate those AXI GPIO blocks from the PYNQ side of thing. The OL object has all the IP stuff in there. You can say something like OL dot. If you hit the tab key, it'll launch the autocomplete. I will say that the autocomplete running on the embedded RDZ7 is not super fast. So if you get kind of deep nested off in there, you might have to wait 30, 40 seconds for this to come up. But this has got the different stuff. Like it's got like our AXI GPIO instance, our debug bridge instance, and that's pretty much it. And all this, and using the PYNQ libraries to manipulate this stuff, all that stuff's well documented. We can just run that. So, like I assign I/O control to our channel 1. If you remember, it's that 2-bit value where you got the count and the clear, and then we have an I/O load, which is just our channel 2 of that AXI GPIO. And the write command is really simple. They're set up to be output only, so you will only ever be writing to them. You just give it a value and then give it a bit mask. And it's pretty cool. We can start the counter counting. And if we have 2 hardware ILAs here. I guess I should cover the triggers. Yeah, let me cover that first. On these trigger settings, because I did have them cascaded, like they're cascaded one to the other, to make that work, you'll have to set up hardware 1, which is the parent. It will have a trigger out mode, and you'll need to set that to trigger only. Capture mode is always, I may as well use the maximum window depth that's already there, and then trigger in the middle of the window. Likewise, hardware ILA 2, its trigger mode needs to be set to trigger in only. Otherwise, it's not going to work. And the same thing, capture mode is always biggest window depth, and then just center it in the middle there. We can get rid of these. Let's try and get these a little bit better organized. I'm not a fan of the UI of this thing. It seems like I feel like I'm always fighting it. All right, so yeah, we started the counter. We should be able to see it run. Oh, it's waiting for trigger. I did not mean to do that. Trigger immediate. Yep. Sweet. Yep. It's counting up from 0 to 65,000 something. It's giving us our one shot there. Cool. You can see that the count enable is set high. So what we're going to do here is I'm going to arm this trigger. And so now hardware ILA2 is waiting on the trigger from hardware ILA1. And speaking of its trigger, there we go. It's like, where's my trigger? You're going to want to set up a trigger on XS16 load enable, and you're going to want to set it equal to R, which is a transition from 0 to 1. That's what we're looking for. So we're looking for load enable to go from 0 to 1, because we're trying to capture a load event. And so once you get your trigger set up, this thing's waiting for a trigger. Now this one's waiting for a transition from 0 to 1 here, and we're ready to fire it off. I've got all the same information that I just gave you embedded right here in this notebook, which is going to be part of the repo, and all this stuff will be posted in the description down below. This should write or load a value. It should let's see here. Yep, it enables the counter, and then that sets the value of the load value, and then also sets the load enable. I'm not sure if I have to do this. Right, I'm not sure if I could just write a 0 here and everything would stay latched, but right now I'm still including that on that side. So this is the kind of stuff where it's good you can learn and test and see how it actually works very quickly. Anyhow, we'll run that, and that should set off our trigger. Boom, look at that. Beautiful. Here's our load event. We'll get our load signal. Here's our value to load, and it's dead. That's just the value from right here. And then, yeah, our counter was operating normally before the trigger, and then boom, there's a trigger event, and the value of the counter after the trigger event is dead. Sweet. So that's just kind of a basic rundown on how it works. I'm going to have to clean up this code a little bit, but it really is that automatic, at least if you're using PYNQ on a Zinc 7000. It's been a while since I've done the YouTube thing. Like I said, I am currently looking for work, so if anyone has any ideas or knows of anyone, just let me know. And also, if this is something that you might want to follow along with, if I ever find any more interesting tidbits to share, then just let me know in the comments below, and see y'all next time. All right, appreciate y'all for watching.